Hello and welcome back. In the previous video, we spent a lot of time understanding transaction grained fact tables, probably the most common type of fact table you'll encounter in real world data warehouses. We looked at how they store detailed business events, how fact tables connect to dimensions, how grain affects the modeling decisions, and why different business processes usually need separate fact tables. But transaction fact tables are only one part of dimensional modeling because not every business question is really about individual transactions. Sometimes businesses care about states over time, things like account balances and inventory levels and subscription count at the end of maybe every week or every month. And sometimes they want to analyze how an entire process moves through multiple stages over time, like an application workflow or insurance claim lifecycle. That is where other types of fact tables become important. So in this particular video, we are going to continue our journey into dimensional modeling and explore different types of fact tables. We'll go through practical examples, talk through semi-additive facts, process tracking, multiple relationships to the same dimensions, and a few design patterns that show up all the time in the real world data warehousing projects. So whenever you are ready, let us continue. Now that we have finished talking about transaction grained fact tables, let us move on to the second major type of fact table. And you will commonly use that in data warehousing, that is the periodic snapshot fact table. Sometimes people shorten the name and just call them snapshots or snapshot fact tables. Personally, I recommend using the full term, that is periodic snapshot fact table. The reason is simple. There is another type called as accumulating snapshot fact table, and even though the names sound similar, they solve completely different business problem. So using the full name avoids confusion. So what is the idea behind a periodic snapshot fact table? It's pretty much exactly what the name suggests. We are capturing measurements at regular interval, that is daily, weekly, quarterly, monthly, whatever makes sense for the business. Usually we are measuring some kind of level or status over time. In many cases, these tables are created to make analysis easier compared to working directly with raw transaction data. Instead of digging through thousands or millions of detailed transaction, we store the summarized snapshots at consistent time interval. But there's also another use case. Sometimes the thing we are measuring does not even come from the transaction at all, and we will look at both the transactions shortly. We'll look at both the scenarios shortly. Now let us start with the first one. Imagine we already have a transaction grain fact table called as meal card payment fact. Every time a student uses their meal card on their school campus or college campus, a transaction gets recorded. We track things like which student made the purchase, when it happened, where on campus it happened precisely, and how much money was spent. So if a student spends like $5 on lunch, a new row gets inserted into the transaction system and eventually lands in the data warehouse. Now suppose the university wants to analyze something different, that is students end of week meal card balances throughout the semester. Technically you could calculate this from the transaction fact table using SQL, but it becomes messy and computationally expensive because transaction tables are optimized for detailed events, not for state at a time in point state at a point in time analysis. That is where a periodic snapshot fact tables help. So alongside the transaction fact table, we create another table called as something like meal card end of week snapshot. Notice something important here. We no longer care about the campus food location dimension. For this analysis, we only care about the student, the week, and the ending balance. So the table becomes much more simpler. For every student and every week, we store one fact, that is the meal card balance at the end of that particular week. If you look at the data, we might see something like this. That is, maybe in week 1 you have this much balance, week 2 we have this much balance, week 3 this much, and week 4 we have this much balance. So you can instantly start doing some trend analysis or reporting or forecasting or identifying some spending behavior without having to write extremely complicated SQL every time. And that is really the main advantage of periodic snapshot fact tables. They are designed specifically for analyzing balances, levels, statuses, or measurements at a regular time interval. Now let us look at the second type of scenario. Suppose the university has several reservoirs on campus, and every week they record the water level in each reservoir. Now there is the key difference here. There are no transactions generating this data. There's no transaction table that is tracking maybe every raindrop or every evaporation event or every water movement. The water level simply exists there, and once a week we measure it. So we create another periodic snapshot fact table, that is reservoir level end of week snapshot. The dimensions might be the reservoir, that is the key, and then the week key, and then the last one, that is the water level. Structurally, this table looks almost identical to the previous example. The difference is purely conceptual. In meal card example, the snapshot could theoretically be derived from transaction. In the reservoir example, there are no transactions to derive it from. The measured value simply exist and get recorded periodically. So overall, periodic snapshot fact tables are all about capturing the state of something over time at consistent interval. And while the concept itself is fairly straightforward, there is an important complication that we still need to discuss, that is semi-additive fact. That becomes really important with snapshot tables, so that is what we'll be covering next. Let us continue our discussion on periodic snapshot fact tables and now bring semi-additive facts into the picture. This is where things get a little interesting. If you remember our earlier discussion on additivity, we talked about three types of facts in data warehousing, that is additive, non-additive, and semi-additive facts. Semi-additive facts sit somewhere in the middle. In some situation, you can aggregate them meaningfully, and others in other situations, adding them together gives you completely useless number. And periodic snapshot fact tables are some of the most common places where you will run into them. So let us finally look at a real example. Imagine the business wants to answer a question like, what was Sally Jackson's meal card balance at the end of each week? Now remember, a periodic snapshot fact table, how it works. Instead of storing every individual transaction, it stores the state of something at regular intervals, like end of each day or end of week or end of month. So in our case, the fact table stores an end of week balance and connects to a date dimension and a student dimension. Suppose student key, such as the one mentioned here, that is 732017235, corresponds to Sally Jackson. When we look at the snapshot records, we see something like this, that is week 1, this is the spending, the week 2, in week 1 this is the balance, week 2 this is the balance, and so on and so forth. Pretty simple so far. Now here's the important part. That balance value is definitely a fact. It is something measurable. But unlike sales revenue or quantity sold in a transaction fact table, we cannot simply add balances across time. For example, if we add all 4 weekly balances together, we get $1,552.18 dollars. Now saying that Sally's meal card balance is this much, that is 1,552, makes no sense at all. Why? Because these are just snapshots, not transactions. Each row already represents the balance at that point in time. Adding balances from multiple weeks is basically like adding the same account repeatedly. And that is exactly why this is called a semi-additive fact. You cannot meaningfully aggregate it across the time dimension. But that also does not mean that you cannot do any math with it. For instance, calculating the average balance across those 4 weeks is perfectly valid, which gives you an average balance of about $388.05. That makes sense from a business perspective. Now, Here's another important detail about semi-additive fact. If you lock the time dimension to a single point, say just week 1, then aggregation becomes valid again. Suppose three students had these week 1 balances, that is Sally is having 455.12 dollars, then there's some student B who is having $561.23, then student C, he is having maybe $215.60. Now adding them together is completely reasonable. You could say that the total remaining meal card balance at the end of week 1 was $1,231.98. That is valid because we fixed the time dimension to one specific snapshot and aggregated across students instead. You could also calculate the average balance across students for that same week without any issue. So the key takeaway is this: semi-additive facts can usually be aggregated across some dimensions but not across all the dimensions, especially not time. And that is why periodic snapshot fact tables are so useful. They are great for tracking regularly measured states like balances or inventory levels or account totals and similar metrics where the value represents a condition at a specific moment rather than an event on transaction. Now let us move on to the third type of fact table, that is accumulating snapshot fact table. So far we have already talked about the transaction fact tables and periodic snapshot fact tables, and later on we'll also discuss the factless fact table. But this one is a little different because it's specifically designed to track the progress of a business process that moves through a set of clearly defined stages. The main purpose here is to monitor how long something spends in each stage of its life cycle. In other words, we are interested in measuring the elapsed time between different steps in a process. Typically, this type of a fact table stores information about stages that are already completed, stages that is currently in progress, and sometimes additional metrics collected during the two processes. At any point in time, you can look at a row and accumulating a snapshot fact table and immediately understand where a particular process currently stands. Another important idea introduced here, something that we have not really seen before, is a single fact table having multiple relationships to the same dimensional table. Until now, most examples were simply one-to-one relationships: one student, one employee, one date, etc. But accumulating snapshot fact tables are more complex. A single row may reference the same dimension multiple times. We'll see exactly why that happens in a moment. But let us use, for now, the university financial aid process as an example. Imagine a student applies for a financial aid. The application goes through different formal stages, that is maybe application submission, then it goes for initial screening, then preliminary approval or rejection, and then final approval or rejection, and lastly the payment to the student account. What we really want to measure here is how many days applications spent in the screening, how long it waited for the preliminary decision, and how much time it passed before the final decision was made, and how long payment took after the final approval. That is the perfect use case for accumulating snapshot fact table. Now, just like any other fact table, we'll still need the dimensions to provide the context. So in this particular example, the important dimensions are the student dimension, the employee that is handling the process, and the date dimension. Different employee may handle different stages. One might do the screening, another might handle the preliminary approval, someone else will take the maybe final decisions. So the fact table may need multiple employee references for the same application. Similarly, we also need multiple dates. For example, submission date, screening start date, preliminary decision date, final decision date, and lastly the payment date as well. And because of all those are dates, they all need to connect back to the same date dimension table. That means instead of having just one date key, we now have several date keys. For example, day submitted key, day screening key, day final decision key, or the day payment key. All of this point back to the same date dimension. Conceptually, think of it like this. If you're designing a flat table without dimensional modeling, you'd simply store 5 separate date columns. In dimensional modeling, instead of storing raw dates directly, we connect each one back to the date dimension using separate foreign key. The same thing happens with the employee. Screening employee, preliminary decision employee, final decision employee, and the payment processing employee. Potentially 4 different relationships, all pointing back to the employee dimension table. Finally, when defining the keys, the student key or the date key and the employee key, they remain the primary keys in their respective dimension table. Inside the accumulating snapshot fact table, all those foreign key together form the composite primary key. So compared to the earlier fact tables, this design is much more advanced because it tracks an entire process lifecycle rather than just individual transactions or periodic summary. Okay, now let us continue our discussion by walking through a more detailed example. Earlier, when we introduced the accumulating snapshot fact table, we used the example of a financial aid application process. Here again, you can imagine that the fact table sitting in the center connected to a multiple dimension table, one for the student, one for the employee, and one for the dates. Now, one important thing to notice here is that the fact table has multiple relationships back to the date dimension and the employee dimension. Why? Because throughout this life cycle of a financial aid application, multiple dates and multiple employees are involved. Different people handle different stages and each stage starts on a different day. So let us make it much more practical with actual data. Suppose one of our student, let us say Richard Thompson, applies for $8,000 in financial aid on August 11, 2020. Now the row of the data for this process is pretty wide. So in this example, it visually split across multiple lines, but technically it is still one row representing Richard's entire application journey. So on day 1, for example, the student key is pointing to the Richard Thompson. The application date key, it is pointing to the date, that is 11th of August 2020, and an employee screening key which identifies the university employee responsible for the initial screening phase. At the bottom of the row, we also store the matrix related to the business process. For example, the days in the screening. So value starts as 1 because the Richard's application has just entered the screening stage. Now on day 2, nothing major changes happen. Application is still under screening. The only thing that changes is the day screening value that increases from 1 to 2. By day 3, the screening phase is complete. So now the total days spent in screening becomes 3, and that value is finalized because Richard's application process is moving to the next phase. At this point, we also store a new date, a date key representing the start date of the preliminary decision phase. So moving to day 4, you notice something interesting. Now we have a different employee key, right? The preliminary decision employee key, that is because a different university employees is handling this particular stage of the process. Also notice that the days in the screening is fixed at 3 forever. Now this is fixed, it's not going to change. But now on day 4, we have this extra 1 that has come into picture, and thereby on the day 5, so this is only valid for this particular stage, right? So day 5 rather, it's going to increase from 1 to 2, and this process keeps on continuing until the application is fully completed. And this is where the accumulating snapshot fact tables really becomes powerful. By looking at a single row, we can analyze the entire life cycle of this particular applicant. When each phase started, how many days each phase took, and which employee handled each stage. So for example, screening could take 3 days. Preliminary decision, it will take maybe 4 days. Final decision, it will take 3 days, and maybe the final payment, it may also take 6 days. So all of that can be tracked in one evolving row. And of course, Richard is not the only student who is applying for the aid, right? While Richard's application is moving through later stages, another student may come simultaneously entering the screening process. The same employee who screened the Richard's application might also screen the new student's application as well. That means the fact table is continuously updating multiple rows, each representing a different application at a different stage in a workflow. Another really useful thing here is that we are not limited to tracking just time related metrics. We can also track business value as they evolve through the process. For example, maybe Richard applied for $8,000, but maybe after a review, only $5,000 got approved in the final decision stage. So we can store that this was the requested amount, that is the amount after screening, that is the amount after preliminary review, and the final approved amount, and then the actual amount. So that allows us to analyze not only the process duration, but also how values change throughout the workflow. For instance, again, Richard's application might show 8,000 during screening, then another and preliminary review as well, while another student's application might show $4,000 at the beginning, and we don't know the approved amount until the later stages are completed. So the beauty of this kind of accumulating snapshot fact table is that it makes the process flow analysis much more easier compared to the transaction grain fact tables. Right. Now, earlier we looked at dimension table and understood how they are structured differently in star schemas and snowflake schema. Let us apply the same idea to the fact table as well. Remember, in a data warehouse, a lot of data naturally exists in hierarchies. For example, a faculty member belongs to a department. That department belongs to a college. That is a simple hierarchy. Maybe a college belongs to certain university. Now, in a star schema, all those hierarchy levels are stored inside one big dimension table. So your faculty dimension table would contain faculty information, department information, college information together in the same table. The primary key is usually the lowest level of hierarchy. In this case, something like maybe faculty key. In a snowflake schema, things are normalized instead. So rather than one large table, you'd have a separate tables like faculty dimension or department dimension or a college dimension. Each table has its own primary key and foreign key relationships connecting it to the next level about it. Now let us talk about fact table inside fact table side of the things as well. That is, in a star schema, it is straightforward. The entire hierarchy exists in one dimension table. The fact table only needs a single foreign key, that is faculty key. Now that key connects the fact table back to the entire hierarchy because all the related information already lives inside that one dimension. So if you later want to analyze the data at a department level or college level, you can still do that because everything is available through that single relationship. Now this is where things get a bit of confusing with snowflake schema. You might think that if I have a separate dimension table for faculty, department and college, then my fact table should probably contain 3 foreign keys too. Well, sounds logical at first, right? But in practice, that's not a good design. Technically, yes, it would work because the database won't explode, but the university will continue functioning normally in that case, but it will become very messy and hard to maintain very quickly. Essentially, when multiple hierarchies are involved, things are very much convoluted. They end up with way too many foreign keys sticking out everywhere in every table. So the recommendation is avoid that particular approach. Instead, even in snowflake schema, the fact table usually stores only the key of the lowest level of hierarchy. Again, something like a faculty key. From there, faculty dimension links to the department dimension. Department dimension links to the college dimension. So you can still navigate up the hierarchy wherever needed. Most BI tools, they handle this join automatically behind the scene, right? But if you're writing the raw SQL query yourself, you'd probably join the tables together using a group by command at whatever level you want, maybe at faculty, department or the college level. Maybe I'll prepare a playlist for the SQL as well, that is structured query language. Let me know in the comments down below if you want if you want me to create a SQL series on the SQL. Anyway, so far our discussion has been around fact tables and dimension table and the star schemas and the snowflake schema. We have been drawing the diagrams and boxes that represent different types of tables and showing the relationships between them. But eventually, a raw data warehouse has to move beyond diagrams and actually exist in a database. That is where SQL comes in, especially if your warehouse is built on a relational database system. So now let us shift from concepts to implementation and look at some actual create table example. I will cover all these dimension tables here. You can just go through them. One important thing before we start, the SQL example that I am showing here, it is very generic. They are not tied specifically to any particular platform, for example Microsoft SQL Server or MySQL or Oracle or any other platform, and that is deliberate because in real projects you could end up building the warehouses on many different database systems as well. So the core idea stays the same. You can always add the product specific features later, but let us begin with the first one, that is star schema dimension table. In the SQL, in the first one, we start with a create table and give the table a name, that is faculty underscore dimension. Inside this parenthesis, we define all the columns and their data types and some constraints like not null. After defining the column, we specify the primary key as well. So in a star schema dimension table, the primary key is usually just a single column. In this particular example, that is the faculty key. Even if the table contains multiple hierarchy levels, the dimension still typically uses one surrogate keys as its primary identifier. Now compare this to the snowflake schema. In a snowflake design, hierarchy levels are split into separate tables. So instead of keeping the faculty, department and college all in one table, they are normalized into different tables connecting through relationships. Let us focus on a non-terminal dimension table, meaning a dimension table that still points to another higher level dimension. For example, the faculty dimension table belongs to a department, so it contains a department key as a foreign key. The SQL still defines a primary key like before, faculty key is the primary key, but now we also add a foreign key clause. That clause specifically say that this column, for example, this column department dimension key references another table, that is department key in this table here, right? So the database now understands the relationship between the faculty and department. Now usually foreign key column names match the primary key they reference, but there are exceptions as well. For example, in accumulating snapshot fact tables or some factless fact table, you may have multiple relationships to the same dimension table. In those cases, the column names might differ, and the foreign key clause becomes especially important because it clearly defines which column references what. Moving up one level, the department dimension here, it also follows the same pattern. It has this primary key as department key and a foreign key that is pointing to the primary key of the college dimension table, right? And then this dimension of college dimension table has it's at the top of the hierarchy. That means it does not need any foreign key. It just has this column definition and then one primary key. That's it. Now let us switch to the fact tables. First, consider a transaction grained fact table. Unlike dimension table, fact tables usually have a composite primary key. That means the primary key is made up of different multiple foreign keys together. For example, if a tuition bill fact table connects to a student dimension and a date dimension as well, then the combination of the student key and the date key becomes the primary key. Each of those columns also gets its own foreign key clause pointing back to the appropriate dimension table. So the overall pattern becomes that you have to define the measures or the facts, define the foreign keys, combine those keys into primary key and explicitly reference the related dimensions. The periodic snapshot fact table works almost exactly the same way. Suppose we are storing the weekly meal card balances for student. The fact table might contain the student key, the date key, maybe another dimension key, plus the actual fact like meal card balances. All the dimension keys together form the composite primary key, and each one gets its own foreign key reference. So regardless of whether you are creating the transaction fact tables or periodic snapshots or accumulating snapshots or even factless fact tables, the SQL structure is going to stay very consistent. You identify the key, decide which combination uniquely identifies a row, define that as the primary key, and then use the foreign key clauses to connect back to the related dimension table. The only real complication comes when multiple relationships point back to the same dimension, especially the date dimension table. That happens a lot in accumulating snapshot fact tables, where you may store multiple dates like order date or shipping date or delivery date. In that case, you simply define the multiple foreign key columns, each referencing the same date dimension table.